In the context so far of indefinite integrals, we've learned all of the most important integration rules. So these correspond directly to rules from differentiation, which we learned earlier in these live lessons. The only one that I didn't call out here specifically as we were going over integration was the integral rule, but it's not hard to infer what this is. This was the addition of that plus c whenever we're working with indefinite integrals. Now, we'll move our focus to definite integrals, which actually don't need to make use of that constant rule. I'll show you why right now. All right, with definite integrals, we have pretty similar notation to indefinite integrals, so we indicate what variable we are integrating along. We have a function that we're integrating, but the difference is that in addition to our integration operator, we have included a range. So values, in this case, since we're integrating along x, a start of range and an end of range over which we're integrating for our function. So to make this concept clear, going back to a curve that we looked at earlier, with a definite integral, instead of trying to integrate all of the area under the curve, we're only trying to integrate between two particular points. So in this case, between x1 and x2. So between x1 and x2. Let's go from the abstract to the concrete here and talk about a specific function that we can integrate. So the function is y equals half x. So here's what that curve looks like. It's a straight line. And for every increase in x by 1 unit, we go up half a unit of y. Now let's say we wanted to calculate the definite integral over the range where x equals 1 up to where x equals 2. So this area that I've filled in here. In that case, the precise notation that we would use is here, where we are putting in the variable that we're integrating over, x. We have our function, half x, and then we use the integral symbol, and we have it ranging from 1 to 2, which corresponds to the range that we would like to integrate over. To make sense of calculating this definite integral, let's start off with calculating the general indefinite integral. So we can use the same rules that we learned recently. So for this function half x, if we're going to integrate it, we can move half out in front, which leaves us with just x. And when we integrate x, that gives us x squared divided by 2. And don't forget that plus c constant that we have anytime we're doing an indefinite integration. So we can simplify this term a bit here. Half times x squared over 2. We multiply the numerators and the denominators, leaving us with x squared over 4, x squared over 4 plus c. Nice. To move forward with our calculation of the definite integral, we can start off by calculating what the integral would be for this chunk of area here, where x is equal to 1. So to do that, we take our formula from here, and we sub in 1 for the x value. So 1 squared leaves us with 1. And so our final expression here for x equals 1 is a quarter plus potentially some constant c. So we can see a visualization of the area being occupied by this calculation. So it's 1/4 units squared, this triangle here. Now we can do the same thing where x equals 2. So we can calculate the area of this triangle here by substituting 2 in for x and working through the arithmetic. 2 squared divided by 4 will leave us with 4 divided by 4, which is 1 plus c. And that corresponds to 1 unit squared here now under our curve. Armed now with our 2 indefinite integrals at x equals 1 and x equals 2, we can calculate the definite integral over the range of 1 to 2. To do that, we simply subtract the indefinite integral for the end of the range by the indefinite integral for the start of the range. So 1 plus c minus 1/4 plus c. So this corresponds in our diagram to the full big triangle chunk minus the little triangle chunk, which leaves us with the area over the range of 1 to 2, which is exactly what we were looking for. Now the neat thing here is that when we perform these mathematics, the c's cancel out because we have plus c minus c, and for the only other terms remaining, 1 minus 1/4, that leaves us with an overall definite integral of 3/4, indicating that the area under the curve here is 3/4 units squared. Now, I do have some paper and pencil exercises coming up where you can practice what we've learned about both indefinite and definite integrals. But first, let's also see how to calculate integrals in Python code.